B.2, estimate the cost. Here, we use the term cost. What do you mean the cost? The cost here, we mean the computation cost. When you do computation, there is a cost you need to pay, right? Yeah. In execution time, right? So in many different ways, we can describe that cost. Yeah. All right. So here, because later in many different situations, we may use the term like this, yeah, computation cost, yeah, because everything, there is a cost. If you want to do anything, you need to pay some cost. Yeah. Here, the same idea. Yeah. All right. So we just complete counting number of additions. Yeah. Next, we need to count the number of multiplications. Yeah. All right, so to do the count the number of multiplications, okay, yeah, we use the same way to do the counting, although it is a little harder than counting number of additions, but still not very hard. Yeah. All right, so now let's count the number of multiplications for each term. So here, this is a representative general term in the original polynomial. No, it's a general representative. If we can do for this general term, then we can do for all the terms. All right. So that's the usual way we deal with, many different terms with the similar properties. Yeah. All right. If we can get an answer for one general term, then we can get answers for all the terms. We just add up all these numbers, so we get a final answer. So that's the idea. Yeah. All right. So now let's do the work. Yeah. Solve a general problem. This one. Okay. To count the number of multiplications. Yeah. Here, I want to introduce a simple strategy, but it is very useful, very effective, and we will use this strategy many, many times. Okay, so what strategy we like to use here? Try simple examples to get some idea. Work on simple examples. Because this general term looks a little abstract. Okay, although you can still work on it. Yeah. But usually when you work on abstract question, it is relatively hard. If you can work on concrete question, then it is easy, much easier. Okay, all right. So let's work on some simple concrete cases, so we can get some idea. The first concrete simple case, a1x. How many multiplications do we need? Just one. a1 times x. Just one multiplication. Okay, so we can get an answer easily. All right. Second simple case, a2x squared. How many multiplications do we need? Okay, 2. Yeah, because a2 times x times another x, right? So here you need to use 2 multiplications. All right, so let's do one more so we can get idea. Okay, a3 times x cubed. How many multiplications do we need to calculate this term? Okay, you can see 3, because a3 times x times x times x. Okay, yeah. So let me write explicitly. a3 times 1x times second x times third x. There are 3 dots, 1, 2, 3 dots. So there are 3 multiplications. Okay, so we come in this way. So you can see a1 term, 1 multiplication. a2 term, 2 multiplications. a3 term, 3 multiplications. ak term, how about that? Okay, I think you can use induction to get that answer because you find a rule. You observed a rule for the general term. Okay? The answer is k multiplications. So that's simple. How about that? Okay? Yeah. So our answer, k multiplications for each general term. Okay? With this answer, then we can put things together. Okay? So all the terms that require multiplications. So we put here. Okay? The first term 1, second term 2, 3, and so on. The last term n multiplications. So we add up all these n numbers. What's the answer? Okay? Here, recall, so if you still remember this formula from your discrete math, find the summation of arithmetic series. Summation formula of arithmetic series. This is the formula. 1/2 times n times parenthesis n plus 1. Okay, simple formula. Yeah, here we use that directly. So the last step now, total units of time to do the evaluation. Total units of time. Yeah. All right, so this is the answer. Yeah. Okay, yeah. And yeah, because each addition you multiply by 1. Okay? Each addition you use 1 unit of time, but each multiplication you use 10 units of time. Okay? So you do multiplication 1/2 times 10, that's 5. So you get 5n times parenthesis n plus 1. Okay? So yeah, you do some simplification. So you get final answer expression, 5n squared plus 6n. That's our performance number, total performance number we can use. This is an objective measure. It does not rely on your computer, your hardware, right? Yeah, even your program. It does not, because to implement this same algorithm, 100 people may have 100 different ways, right? Yeah. So it does not rely on the program implementation. Okay, yeah. All right. So here the question, our next question. How to reduce this number? Can we do better than this? Yeah. Can we do better than this? Right? Yeah. So that is an important aspect in algorithm. We should try to improve our existing algorithms. Okay? Yeah. But at this point, it is very hard to get that answer. We don't have enough information. So we need to do more work to get this answer. Yeah. All right, so but here we want to move to the next step. Improvement. Algorithm improvement. So we need to have some strategy. Here you can see in my part 1, I talk about the importance of strategy. Strategy, execution. So we start work on strategy, then execution. Okay, here, strategy first. Improvement strategy. We need to do observation. Observation is very important. When we start to work on some problem, we need to do some good observation on our problem. The reason is we want to get some good property we can use. Okay, so here we need to have some useful property. We can take advantage of it. Yeah. All right. Cost ratio. In our observation, we look at this quantity, cost ratio number. What's that? Unit cost for multiplication over unit cost for addition equals 10:1 ratio. That's important property we have in our observation. Okay? All right. With this observation, we can get a natural conclusion. Yeah. Focus more on multiplications. When you try to pay some effort, we want to focus on multiplication part because we will get much better payoff. Okay? We will get much better result. There is much more room to do the improvement. Here you can see this number is much bigger. We have better chance to reduce it. Yeah. Because our goal is to reduce this number. The first term already a very small number. It is very hard to reduce it even more, right? Yeah. So the natural conclusion in our strategy, put our effort on multiplication reduction. Okay, yeah. So based on the strategy, reduce the number of multiplications. So you can see that's our direction. Okay, all right. Next, we need to work on it. How to reduce the number of multiplication. So that's the important step. Yeah. All right. Implement the strategy. This time, execution, right? Implement. So this means we need to do the execution step. Okay? Yeah. Execution step, really important. Okay. All right. Yeah. All right. The strategy, reduce the number of multiplications. Yeah. We noticed that. Yeah. First term, very small. Second term, compare with the first term, much larger, so we have bigger room to do the improvement. Yeah. All right. Strategy, it gives us direction to go along this direction. Okay? Yeah. There are many different directions now we identify. So this direction is the best way to go. Okay? Yeah. That's the first thing. Second, execution, how to get there. Even you know you should along this direction, but you need to have some good way to do it. Okay? So execution part also extremely important. So that's from our part one. So we know that its importance. Yeah. All right. Question. How to reduce the number of multiplications? That's the question we need to answer at this point. Yeah. All right. Strategy. We need to use strategy. So you can see we need to use various strategies. Here, how to solve this problem? We need to have some strategy first. Okay. What's that? We used that before. We just used it recently. Yeah. Let's use it another time. Study a simpler case. Remember, so when we count the number of general terms, ak times x to the kth power, we work on some simple cases, right? Here, we do the same thing. Study a simpler case to give us some idea. Based on that observation from this simpler case, we try to get some rule, general common rule, so we can generalize to the general term. So that's another good, effective problem-solving strategy we frequently use. Okay. All right, so let's do it. Let's work on it. Do the work here. Yeah. Consider n equals 2. That's a simple case, right? N equals 2. Very simple. Yeah. We do not consider n equals 1, n equals 0. The reason is too simple. If it's too simple, nothing to work. If you have nothing to work, then you cannot get any valuable observation, right? So we need to get something interesting from the example. So that's why although we want to make the case as simple as possible, but at the same time, we also want this case is meaningful. Okay? Simple, but a meaningful case, right? All right, so here, let me add one more thing. A simpler case, but it should be meaningful. Also important. Okay? Meaningful case, also important. Okay? Here, n equals 2, we have a meaningful case. Because here, our polynomial is a quadratic polynomial. Okay? Degree 2, quadratic polynomial. Okay? The name is not very important, yeah, but here we just work on it, quadratic polynomial. Okay? Yeah. All right, let's do the critical observation to find a useful property here. Let's look at the last two terms. Last two terms, because they contain multiplications. The first term, there is no multiplication, so we don't look at it. Okay, so the last two terms, they both contain multiplications, operations. All right, so when you look at that, do you have an idea what is the most obvious property you can see? Can you see that? Yeah. All right, I cannot hear from you, but let me see if you get the correct observation. Yeah. Common factor x. They both have this common factor x. That's the property. We can take advantage of it here. Okay? Common factor. When you have a common factor, what you can do, right? Yeah. All right, so here, let me give you another general problem-solving method to use. Transform the problem. Given a problem, so sometimes we get stuck. We don't know how to work on it. It happens frequently. When that happens, one commonly used method is do transformation on the problem. You change the form. You change it to a different form, equivalent, different form. After you do the change, then you can get insight. You can find a new property. You can get insight. You can have a new idea. You have a new view on your problem, and you can get some solution on it. Okay, so let's do it now. We change structure for new outcome. We change the structure of the original expression. When we change structure, we see something useful. If we do not change structure, we cannot see. Okay, some good property is hidden. It is buried somewhere. We cannot find it. Now we change the structure to reveal that hidden nice property. So that's what we are going to do here. Yeah. All right. We do factorization. When we do factorization, we change the structure. We reveal the hidden property, and we get the insight. All right? Yeah. Let's do it here. All right. Sum of the last two terms, because they have a common factor x, so we factor it out. Okay? So we get second equivalent expression. This equivalent expression has a different structure comparing with the original one, right? The structure completely different. And this new structure gives us new property, new insight of this problem. So what's that? So let's look at it in this way. Let's do the counting. count the number of multiplications. Okay? From the first instruction, how many multiplications do we need? Now, if we count the number of multiplications from the second expression, this one, tell me, how many multiplications do you have? Right? The first one, x times parenthesis, okay? Whatever it is inside the parenthesis, one multiplication. Okay? Second one, a2 times x, the second multiplication. That's all we need. We only needed 2 multiplications. So look at here. That number is different. After we change the structure, we change the number of multiplications needed to find the answer. Okay? So now you see the difference, right? You see the improvement here. Okay? Yeah. Conclusion. Our improvement. After factorization, doing the transform, we use the factorization method to transform the original problem. As a result of the transformation, right, our gain on performance improvement from 3 multiplications to 2 multiplications. The improvement is 50%. Is that a good improvement? 50% improvement. Is that a good one? Right? With respect to this one, 50%. Okay? Yeah. If with respect to this one, then the number could be different, right? 1/3 improvement, right? You can argue in this way. With respect to 3, we can argue 33 improvement. But it is still a good number, right? Still a good number. Good percentage. Very high percentage. Okay? Yeah. So here you can see, yeah, by working on a simpler case, simple but meaningful case, we get something very useful, very important. And this observation, the rule, the property, from this simple example, we can apply it to the general case. Okay, so our next question, can we generalize this idea to the general end? Right? So in our next video, we will do this. Okay, we will do the generalization, and we want to find the final answer. Okay, all right, so let's stop here, our B.2.